All right, so in this video, I'm gonna give a quick summary of all the topics and skills that you should know and be able to do in this chapter to do well on the chapter 6 test, where where we're dealing with random variables. So this is just gonna be a simple summary. I'm not gonna go into super deep detail, but I am gonna go and make sure I address all of these learn objectives. I broke it up into 11 learn 11 goals that you should have. So take a minute and pause the video and write these down so you can use this as a reference study sheet when you're cramming or preparing last minute for that final or test. So let's get going. So the first thing we're gonna have to be able to compute probabilities using the probability distribution of a discrete random variable. So we gotta know what discrete random variable is. So a discrete random variable is essentially a variable that takes on whole values. So we're going to use x as our discrete random variable. And x could, be all these values. We have, let's say, x1, x2, x3, x4. So they're variables that basically could be like number of siblings you have, the number times you eat per day, how many pairs of shoes you have. These are values that aren't going to be like 1.1, 1.7. You can't have like 1.7 siblings or 1.5 pairs of shoes. These are going to be whole numbers. So each of these have a probability, probability of P1, P2, P3, P4, and so forth. So this is a discrete set of variables because they take on whole numbers or numbers that have gaps between them. Now these are still going to have to add up to 1. So the total probabilities are going to have to add up to 1, and each of them will have to be between 0 and 1. So that's always going to be true in order for it to make sense. Now when we're calculating the mean or the expected value of a discrete random variable, we're going to use this formula, which is given actually in your formula sheet, which I have right here, to make sure you have it as reference. The mean is going to be represented with this symbol mu sub x, or we say expected value of x, which is going to be the sum of each x value times its corresponding probability. So make sure you know how to use this notation. So it's a weighted average. Expected value is a weighted average because the chance of each value occurring is not going to be the same. It's not like where you roll a die and the chance is 1/6, so you just divide the total by 6. No, you have to take into account the weighted probability. So when we're interpreting this, we're just going to basically interpret it as as we would normally with a mean, what we say mean or average when we're talking about normal variables that we're used to in everyday life. Now there's also a standard deviation for discrete random variable that is also given in your formula sheet right here, sigma sub x. It's going to be actually kind of tedious, especially if you have a lot of values, so make sure you know how to interpret the notation, because that's all it really is. Once you know the notation, you can just plug values into your calculator and let it do the work. But if you don't know what these symbols and letters mean, then you're going to be very confused. So it's a square root of the product of the sum of the square differences between each value and their means times corresponding probabilities. So let's go to the first example we did in our notes, so we can get a clear sense of what's going on. So then where we had the problem that we dealt with data that showed the number of languages that students at this school spoke with the corresponding probability. So this is a discrete random variable. Languages took values of 1, 2, 3, 4, 5 with these corresponding probabilities. And we would then calculate the expected number of languages that a student spoke by using the formula that I just went over. So it would be, again, x1 times p1 plus x2 times p2 plus x3 times p3. So we multiply the corresponding probabilities by the number of languages. So one language times the probability of speaking one language, plus 2 times the probability of speaking 2 languages, plus 3 times the probability of speaking 3 languages. Add them all up, and you're gonna get 1.457. So we say that if we were to randomly select many high school students, the average number of languages spoken would be about 1.457. Now, make a note that this value doesn't have to actually be one of the discrete values in set of data. So it could be a decimal, that's fine. Now let's look at the standard deviation of this. The standard deviation, when you use the formula, again, it's tedious, but here's the work. Make sure you know how to use it. And here it is, broken down. We eventually get the square root of 0.457, and it still means the same thing as standard deviation that we've been used to, which basically tells you the average difference from the mean number of languages spoken. So we see the number of languages spoken by a randomly selected student will typically differ from the mean by about 0.671 languages. So again, it doesn't have to actually be one of the values in the set of data. All right, let's look at the next objective we got to know. So you got to compute probabilities using the probability distribution of certain continuous random variables. Now, all this is actually dealing with is what we learned in chapter 2, where we have a distribution that we've only really learned normal distribution. So you're going to get a variable that's normally distributed with some mean and some standard deviation, and you're told maybe like find the probability, find the probability that x is more than, let's say 10, let's say, and 10, let's say 10's over here. So you're basically just finding the area underneath this curve from 10 to the right. And again, we've only learned normal distribution so far. So all you have to do is use, your normal table A, to calculate the probability of a standardized score being greater than whatever value you have. Let me just go back quickly to the example that we did in our notes, where we were looking at the weights of these 3-year-old females. And again, this is an example of what we're talking about with the continuous random variable. Has a mean of 30.7, standard deviation 3.6 pounds, and is normally distributed. And we were trying to find a probability that a randomly selected 3-year-old female weighs at least 30 pounds. So the area to the right is 30 underneath this normal curve. All right, let's look at now how we describe the effect of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. Now, this is actually pretty similar to what we did in chapter 2, where we had a variable, let's say x, and we want to change x into y, to another, variable, y. And we have this general formula where y is going to be equal to a plus b times x. Y equals a plus b times x. We call that a linear transformation. That's how we address it mathematically. Some textbooks have the a and b capitalized. It's fine if you have it like this. I think mine actually has it like this. Now, what we need to know is what's going to be the mean of y when you apply this, transformation with this equation. Well, the mean of y will simply just be equal to a plus b times the mean of x. So you apply the same formula where we multiply by b and add a, as we would do normally to change x into y. Now for the standard deviation of y, what you have to only worry about is multiplying it by b. And standard deviation has to always be positive because it's a measure of spread. So we multiply by the absolute value of b times the standard deviation of x. So that's what we're talking about. So a simple example, the very common example is when we're changing, like, let's say, from some, when we're talking about temperature, and we're changing from degrees Celsius to Fahrenheit, or let's say Fahrenheit to Celsius. But let's say we're going from let's say x is Celsius and y is in degrees Fahrenheit. So we want to change from Celsius degrees to degrees Fahrenheit. Well, the equation, which you guys should know, especially if you go traveling, will be that the degrees in Fahrenheit, which is y will be equal to 1.8 times x plus 32. This is the actual equation for the change from degrees Celsius x into degrees Fahrenheit y. And so then that means that the mean of y will just be 32 plus 1.8 times the mean of x. Whatever the mean of the temperature is on that day, we can find it by just doing this. Now, if you want to find the standard deviation of the temperature in degrees Fahrenheit, given the standard deviation in degrees Celsius, you would then just multiply by 1.8. You just get 1.8 times the standard deviation of x. So that's what we're talking about here. All right, let's look at the next one. Now we have we need to understand what the mean and standard deviation of the sum of or difference of independent random variables is going to be. Like, what's going on there? So what we're going to be dealing with here is if, let's say, we have another variable that's created by adding or subtracting two other variables. So let's say we got let's say we're talking about high school students. So let's say we're studying the number of words spoken on average by students at a high school, and we're breaking our data into grades. So let's have F as the number of words spoken by freshmen, S as sophomores, J as juniors, and let's make X as seniors. So we have again the number where we're taking data on the number of words spoken by each student, and we're breaking it down into grades. But what if we want to figure out the total number of words spoken by all the students on on a given day at school? So we're going to make another variable t that's going to be equal to the total sum of the words spoken by all the students, which will be F plus S plus J plus X. Now, in order to do calculations involving t, and again, we're going to say that all these are normally distributed. Let's say we want to find, okay, well, what's the mean of t? What's the mean number of words spoken on average by a student at high school? Any student, again, t is the total number of words spoken by all the students. Well, this would be equal to the mean number of words spoken by a freshman plus the mean number of words spoken by sophomore plus the mean number of words spoken by a junior plus the mean number of words spoken by a senior. So the means just add. Means are pretty simple to work with. You just find the mean of t, just add up the means of each of those variables. Now, the standard deviation of t is going to be a little different. If we want to find the standard deviation of t, we're going to need to find the variance and take the square root. Remember, the variance is the standard deviation squared. So the standard deviation is t is the square root of the variance of t. So we need to find the variance of t. Now, the reason we find the variance first is because you can't just simply add standard deviation to get another standard deviation. What we're going to need to do is find the variances. The variances will add, however. The variance of t will be equal to the variance of F plus the variance of S plus the variance of J plus the variance of X. So we find the variances. Once you find the variances, you add them all up, then you take the square root of this total, and then you'll have the variance, and then you'll have the standard deviation and the mean of t, and then you can do your calculations with those two numbers. All right. Now let's look at what about. Now let's look at the final section in this chapter dealing with binomial random variables. So we have to look at the whole type of variable that involves checking these key conditions. So a binomial random variable, we have to check the bins. It has to satisfy 4 conditions where we say it has to be binary, has to be independent, there has to be a fixed number, and we say that the success is the same success or success the same. So what that means is that in order for it to be binary, mean that there's only two possibilities that are, very clear and objective. Like let's say, you flip a coin, it's either gonna be heads or tails. Let's say, you're shooting a basketball, you're either gonna make it or miss it. Independent. You flip a coin, 50% chance it's gonna be heads, 50% chance that it's gonna be tails, and those probabilities don't change even if you flip the coin 10 times. You flip the coin 10 times, and it doesn't matter if you get all heads on the first 5 flips, it's not going to increase or lower your chance of getting heads on the 6th flip. So the probability of success is independent of what happens on any other trial. So next we have a fixed number. We have to say that we're going to flip the coin a certain number of times beforehand. So before we even start our problem, we have to say, okay, we're going to flip the coin 20 times. I want to figure out how many times out of 20 I'm going to get heads. Let's say I'm shooting free throws, and I want to figure out how many shots out of 20 free throws I'm going to make. And the probability of success on each trial is going to be the same. Flipping a coin, the probability is always 50% on landing on heads on each flip. If you're a free throw shooter in basketball, it's typically, going to be, probably somewhere around 70 to 80%. And it's always going to be the same on each shot, take away any psychological, issues going on. So those would be examples of two binomial random variables. Now let's go over a hypothetical example involving shooting free throws. Let's say someone says they claim they're 80% free throw shooter, so they have an 80% chance of making a free throw on any given shot. And they're going to shoot 20 free throws. They're going to have 20 trials. Right? You're like, well, let's prove it. Prove to me that you're 80% free throw shooter. So let's say they shoot 20 and they only make 18 and they only make 12. They only make 12 out of 20. That's only 60%. The guy's, oh, I had an off day. So you're like, well, is that true, or is he lying about his free throw shooting percentage? So what we would want to find out is what's the probability that the number of shots they would make is less than or equal to 20. We say the probability that K, well, depending on what notation you use. I use MPK, but you can say the probability that X, a random variable, is going to be X is what's the probability that X will be less than or equal to 12. So in this case, K will be 12. And we're going to calculate this. We're going to calculate what the probability of this is. And for this, we can actually use our calculator, which is very handy. We're going to use this function called binomial CDF. This is going to calculate the probability that you're going to get 12 or less successes, given that the probability of success is 0.8, and you're taking 20 trials. So for that, we would go into our calculator, go to stats, go over, not to go to stat, actually go to distribution on bars. Distribution, scroll down to, you'll see binomial CDF. PDF is if we're going to say if we have like making exactly 12 free throws. Binomial CDF is the probability that they're going to make less than or equal to something. And the notation is going to go NPK. So N is 20, comma, P is 0.8, and K is 12. So NPK, remember that. And we press enter, and it gives us a probability of only about 3%. The binomial CDF, where we enter, 20, comma, 0.8, comma, 12. This gives us only a 0.03 chance of this occurring. So this says in context that if he really is a 80% free throw shooter, the chance that he's going to make 12 or less free throws when he shoots 20 is only about 3%. So it's possible, but it's low. So we're definitely going to be a little suspicious of him. All right, now let's look at the mean and standard deviation of binomial random variable. That's pretty simple. It's just, again, given to you in this formula, NP and standard deviation as this. So we simply just have to plug in our values for N and P that we're given, the mean of X will be n times t. In this case, it'll just be 20 times 0.8, which will be 16. And standard deviation will be, and my calculator do the work, I'm gonna get about 3.58. So what this means is that on average, if he shoots 20 free throws, he's gonna make 16 of them. And his standard deviation of 3.58 says that he will typically be off by 3.58 shots from the average number of makes. So 3.58 shots from 16, which is the average number of makes, or the mean number of makes. All right, now let's look at finally geometric random variables. So the last one here. So very similar to binomial random variables, except for one slight difference. And in geometric random variables, let's see the next page here. In geometric random variables, what's going on here is that we're basically just waiting until we get one success. So it's still going to be that the event could be a success or not a success. You're still gonna have the same chance of success on each trial, but you're just going until you get a success. So for example, it's like, I'm gonna keep on shooting free throws until I make one. It's not gonna, I'm gonna shoot 20 and see how many I make. I'm gonna keep on shooting until I make one. Or I'm gonna flip a coin until I land on heads. It's not gonna be that I'm gonna flip a coin and see how many heads I get out of 20. You're not gonna flip a coin a certain number of times. And it's actually, I would say it's easier. You just have to recognize when it occurs. But other than that, you really just can apply the simple formula, geometric, in our calculator. You would use this function, it's the geometric PDF function, or the geometric CDF. So we just have the parameters P and K for each of them. And if we want to find the probability, let's say that the probability that he would make his first free throw on his 8th shot, you see the probability of y equaling 8. Or let's say that would take him less than 8 shots to make his first free throw, the probability that y is less than or equal to 8. And that's pretty much all you have to work. So just quickly showing you, going in your calculator again, you go to distribution bars, go down to geometric CDF. You want to find a probability that y is less than or equal to 8. And so it's actually geometric, geomet CDF. So the probability that he would take less than 8, that will take 8 or less free throws before he makes his first one. All we would enter then is 0.8, because we're saying he's an 80% free throw shooter, comma 8, and this is probably pretty high. So it's going to basically be guaranteed that he'll make his first free throw before his 8th shot. And that's all there is to it. So good luck.